So we want to find the area between these four curves. So this is some sort of trig function. This is just a line. And here I have just two vertical lines. This is the y-axis. So I'm just going to try to sketch the situation. And normally I try to find the points of intersection between these guys, but this isn't going to give me an equation that's so easy to solve. So I'm going to try to just graph first. So if I look at this function, I notice that this is just it's like a horizontal squeezing of the cosine function. So I'm just going to try to find the period of the transformation. So we take 2 pi, and we're going to divide by pi over 2 just to see what this function looks like. So here's the pi over 2. And this gives me 2 pi times 2 over pi. So the period of my new function is actually 4. So let's do a quick sketch of this version of cosine. And remember the cosine function, it's going to have a period of 4, so it's going to go down here, here. And okay, and that's the only thing that happened to it. Now this function here is a line. It has y-intercept 2. So maybe I'll draw this up here. And then the slope is negative 2/3. So I'm going to go down 2 and 3 to the right. So 1, 2, 1, 2, 3. So the line goes through this point here. Okay, now x equals 0 is just the y-axis, so that's right here. X equal 4 is this line right here. That's x equals 0. This is y equal negative 2/3 x plus 2, and this is y equal cosine of pi x over 2. Okay, so the region that we're really interested in is this region in here. So a typical approximating rectangle, well, we're going to need 2 because the height of the rectangle really depends on which function is on top. Okay, but these are typical approximating rectangles if I'm integrating with respect to x, which makes the most sense for this function. So let's try to set up the integral here. So the area, the most general form of the integral is that the area from 4 to 0 is going to be given by the absolute value of, let's say, cosine pi x over 2 minus the line. Okay, this is the most general form of the integral. I put the absolute value because, you know, at this point we're not sure which function is on top. So let's rewrite this in terms of top and bottom functions. So if I'm on the interval from 4 to 3, okay, of these x values, my approximating rectangle looks like this. My top function is the trig function, and the bottom function is the line. So here I have top minus bottom. And this will give me a positive height for the rectangle. Now when I go over to this part of the interval, so this is the interval from 0 to 3, I notice that here's my typical approximating rectangle. In the top is given by the line, and the bottom is given by the trig function. So things get reversed. So this guarantees that this is positive and this is positive, which is really what we mean here by the absolute, putting the absolute value around the difference. And then the rest I'm just going to let you calculate yourself. This one I mainly just wanted to set up because I know that the graph might stump people a little bit, or the point of intersection. So I want to look at just one more example. Just a quick one. And I wanted to do this example because it's another example where we have functions of y, and we'll be integrating with respect to y. So again, I'm just going to set this one up. So this is going to be, this is another sideways parabola. It opens to the left. And this guy is, basically it's just the cubic function. If I were to solve for y, which I can do, I would just get the cubic function. So the graph is going to look something like, so the graph of this function is going to look something like this. This is going to be a sideways parabola shifted over. It's going to look something like this. So we want to figure out what these points of intersection are. And I'm going to set my equations equal to each other. I'm going to get y cubed plus 3y squared minus 4 is equal to 0. So this, I don't see an obvious way to factor this, so I'm going to use the rational zeros theorem to figure out the possible zeros. These are the possible rational zeros. So I'm going to try 1. Okay, and 1 indeed is a 0 of this polynomial, and this gives me the factorization. So what we have here is that this is equal to y minus 1 times y squared plus 4y plus 4. And this is just a quadratic. It's a perfect square trinomial. So I know that the points of intersection will be will occur when y is 1 and y is negative 2. When y is 1, my x coordinate will also be 1, and when y is negative 2, my x coordinate will be negative 8. So this point here is negative 8, negative 2, and this point over here is 1, 1. So let's just set up the integral. So remember, if we're integrating with respect to y, it's right minus left. So in this case, my upper bound of integration, so these are my typical approximating rectangles. And I'm going to have right minus left. My upper bound will be 1. My lower bound of integration will be negative 2. These are the y values because we're integrating with respect to y. My right function is the cubic. My left function is the parabola. Or sorry, I think I have it backwards. My right function is the parabola. And my left function is the cubic. So And this is just the setup here. So if you and then you can just go through the you know, integration here. So this one I said